if I go too long. So I'll go quickly through an introduction. Again, methods are very similar to what we've seen before. I will focus mostly simulations, but just to show really the kind of things that you can do with the implementation that I'm proposing, and then the application to a cystic fibrosis data set, just to change again from the blood pressure topic, which seems very common, and then some conclusions. This is a joint work with a lot of people, and many of them are here, and I'll thank especially Angela, Ruth, that is sort of there, Jessica is here, and then we have collaborators on the statistics side and also on the cystic fibrosis setting. In terms of the introduction, I keep this slide just because it reminds me of my journey with individual variability that started fairly recently, just a few years ago. And essentially, again, the idea is to model not only the variability in the longitudinal setting, but also try to see whether this variability can be informative when we model the time to event. So what many people might do in clinical settings is to reduce that to a simple summary statistics. For example, for each subject, you take standard deviation and then use that in a time to event model. This approach has some limitations, and especially for the association terms, Jessica has done a lot of work in that in her 2019 paper, so I'm not going to cover that. What I want to mention is that the application in the cystic fibrosis actually, as in the blood pressure literature, there is this big focus about within individual variability. A paper in 2016 by Morgan and colleague highlighted the need for modeling within individual variability of lung function, which is one of the main outcomes of interest in the cystic fibrosis, and they highlighted the need for modeling this kind of variability to understand the disease progression. And the approach that they took is something a bit more complicated than this, essentially splitting the time window into two parts. In the first part, you measure some summary statistic, and then you compute the variability with respect to the summary statistic in the second. So we said, okay, let's try to use the joint model, and I feel by now we're all kind of found the need, the importance of that. This is just some related literature. Again, Jessica's paper in 2019, Sonia's work with BAMLs, where they have the possibility to model the variability. And I mentioned also JM Stan here, just because this will be relevant for me later when I'm talking about my own Stan implementation. So the JM Stan, and it's what you find in the R Stan ARM package. There is a joint model implementation, and that has been first developed by Brillman, and then essentially I'm sort of working on the code by Brillman to make it suitable for our purpose. And then in the frequency side, we have what Helen presented in FlexVar JM and the JMH. And in particular, as Helen said before, they're working on the setting with the univariate longitudinal marker and competing risk. So what I'm trying to do here is variation of all of this, essentially going with the multivariate longitudinal outcomes. In particular, now I have M, the number of outcomes equal to 2, because bear with me, and then within individual variability and the correlation between the outcomes controlled through that. We have also B-splines for the hazard function, for the log baseline hazard function, and we are essentially implementing all of this in Stan, again, following what is the structure in the package R Stan ARM. So it's a slightly different implementation, for example, what Sonia proposes. So, and this is based on Stan, so Hamiltonian for I'm just gonna skip this part. I'm just gonna clarify a bit the notation. The model is very similar to what we have seen already. I just want to focus on the fact that I will use superscript to identify which model and which outcome I'm talking about. So in this case, mu k will refer to mu of the case longitudinal outcome, where I stands for the I subject and J for the J's measurement or J's visit when the observation is taken. And these notations is very similar to what Sonia especially uses in her work. So we have essentially defined these linear predictors for the specific parameters of the distributions here. And here you can have fixed effects, you could have random effects. For simplicity, I'm telling you already, I'm keeping this very light, especially because we're trying also to disseminate these kind of models into the cystic fibrosis community. So at the moment, we're looking only at the random intercept set, very simple, but you could extend that. Again, we use a correlate. We use this kind of decomposition of the covariance matrix so that we have a correlation matrix and a diagonal matrix with the standard deviations of the random effects. And obviously, the random effect in this case will essentially put all these models together and will also, in a sense, include the correlation between the different multivariate outcomes. In terms of time to event some model, again, I'm not doing anything different from what has been proposed before. So again, a proportional hazard structure where we have some association with the longitudinal part. And in particular, we will focus, I have it here, we will focus on either random effect association. So this is essentially the random effects, but in this case, the random effects include both the random effects for the mean submodels and the sigma submodels. So we also take into account the association with the variability. We can have a function of a current linear predictor, and in this case, again, this is a vector including the current, the mean, and the current sigma for, in this case, actually log sigma, or we can, say, yeah, I have both current value and current and linear predictor in a sense because we're modeling log sigma, so you might either use log sigma in the model there or sigma. But yeah, just to, and there is much more that can be done in that. And again, I refer to the paper by Sonia, who has extensively looked at this problem in a more flexible way. Assumptions, we know that in all this setting, we have the share random effect structure. So the random effects are the one that put the blocks all together, and there is conditional independence on the random effects. I'm just going to skip over the details because, again, these are very familiar with what has been done already. I just want to point out that essentially we're replacing wherever you see the sigma ijk, we now can use sigma ijk, we can use the linear predictor here. Again, we have the same problem as discussed before, that we are dealing with that nasty integral, and therefore we use Gauss-Krumm-Roth quadrature rules there. Prior distributions here, again, I'm not inventing anything. I'm just using standard prior distributions here. So I'm going to skip over that. I'm just going to show what you can do with this kind of data. So I tried to simulate from this joint model where I have actually some association with this variability. I just want to briefly discuss how I did it, just to make sure that everyone is on the same page with that. So essentially, I first generated some random effects from a multivariate normal distribution. And again, at the moment, I have 4 random effects, 1 random intercept for each of the submodel, mu1, sigma 1, mu2, sigma 2. Then I generate the survival times using a Cox exponential specification, but in my function, actually, I can use also a Cox-Gompert specification. And then I use this probability integral transform. So I use this UI from a uniform distribution, and these are my time to events. How I generate data, in this case, I'm using random effect association, but again, I can change it to a linear predictor association, for example. Generate censoring time using a uniform, and if the censoring time comes before the event time, I'll declare them to be censored. And then when I have that, I essentially generate the visiting schedule, and to keep things easier here, I'm just using a regular setting. And then when I have the time for the visits, I just generate the data using the Melson specification. So in this case, I'm going, again, very simple settings. I just have, actually, I need to check here because I changed it very recently. So I had the first setting where my mean specification was just a fixed effect of time and random intercept, but I can also add some other covariates there. These are the data just to look at the parameter settings that I've used are nice and make sense, sort of. These are the outputs. I'm not going to go through this table a lot, but this is just to say the input values that I use for the random, for the standard deviations of the random intercepts. These are the fixed effect of time, and these are the associations. And it's good. It's okay. And in this case, I think I've generated 500 observations for 500 subjects, and I can't remember how many of these. I think several thousands of longitudinal measurements. But obviously, those numbers depends on the parameters that I use, because of the hazard changes, how long those people are observed for. I have something to check posterior predictive checks. I've done, yeah, and this is the kind of output that you could get for a single person. You'll get, in this case, you get the black line is the data that I've simulated, and the red lines are my predicted values with the and the red shaded area will inform about the variability. In this case, for this data, I generated variability to be increasing over time for the first outcome and decreasing over time. Baseline hazard, just to show, because this has given me a lot of pain, but and I make it to work. I generated a constant baseline hazard, which I can now reconstruct. And the way in which I fit that is using these lines. So I get that flexibility. Application to the data. Now I'm going to present this data about the UK cystic fibrosis registry data. So this contains a lot of information about people with cystic fibrosis in this country. It's and in particular, there is this CF Happy-Net initiative to make those data ready for research and available to those who are interested, as long as they submit a project proposal. In this case, I focused on a specific subset of it. I'll focus on all the adult women, so 18 onwards. And what I've done is I've introduced administrative censoring at 50 years old, because most of the people have those observations for that period. And I think 50 is also some sort of close to the life expectancy for these. These observations were taken up to 2020. And in particular, what I've done, I'll put it out now, there is another variable, event variable of interest here, that is transplant. And transplant will change the longitudinal outcomes quite a lot. So what I've done is to restrict myself. For those people who were transplanted, I just take the longitudinal observations before transplant. So just to deal with that. These, in my case, are the Kaplan-Meier curves by genotype. I have this information, and in particular, I took it binary, so whether they are homozygous or not, just to show also the numbers of the people at risk at the start. This goes over time. Again, here I'm presenting a very simple model where my two outcomes of interest are FEV1, which is measured in liters. For those of you who are familiar with cystic fibrosis, an outcome that is often looked at is percent predicted FEV1, but in this case, we're restricted to this one. And then BMI as an indication of nutrition status. And I use as a simple model for the longitudinal part, just a linear effect for age and the random intercept, but still the kind of posterior predictive checks for the longitudinal part seems not too bad. And these are the outputs, for example, for two subjects. For two subjects. For Y1 is FEV1 and Y2 is BMI. And even if there is some, wiggliness there, but the model tracks at least the trend and variability. And what I want to mention also, the fact that in Meltem you might say, okay, is it worth it to add this kind of random intercept in the scale submodel? And you look at these parameters, and this should be sigma 2, and they're okay, far from 0. The other stuff, you can look at the correlation between the random effects, and you can highlight, for example, the correlation between the mean of FEV1 and the mean of BMI, and so on. Just looking at the association, This is the interesting part, I think, because we have that for both for FEV1 and BMI, if their mean value, if their current value, if the current value decreases, the risk increases. Am I right? Yeah. While for sigma 1, if the variability increases over time, you also have increase in the hazard. So this is kind of something that possibly it has not been discussed before. And in this time event swap model, I have also other covariates like your birth one. This is the baseline hazard. I'm running out of time, so I'll go skip currently. So this code handles a multivariate setting. At the moment, only 2 longitudinal outcomes and 1 event variables. And in terms of the application, we have found some interesting features about the within individual variability of FEV1. While for BMI, we haven't seen any relationship with the BMI variability. I'm working now on the code, not on the stand code now, but mostly on the R functions, just to complement with that and to bring the outputs in a nice way. So hopefully that will be available in a few weeks/months. And we want also to try, for example, to study some setting like cardiovascular disease, because everyone is interested in blood pressure variability. And this is me. Thank you very much. I'm happy to take your questions.